system is called causal. A system is a causal system if its impulse response is 0 before time 0. After time 0, things can happen. Before time 0, sorry, no response. Okay, so that's the idea of a system being causal. A system only produces output right at the moment or after the system receives an input. Okay, before the system receives any input, it doesn't spontaneously produce any output. That doesn't happen. Okay, causal. 这样有没有一点感觉 cause? Because the system has a cause, then it produces response. Okay? So just to simply draw a picture, an h of n might look like this. H of n at time 0, there is a response, and then later the response can last for a few moments or indefinitely. Okay, but any time before time 0, everything should be 0. No response before time 0. What is time 0? Time 0 is the moment the system receives the delta function. Okay, so delta function. Okay, let's emphasize again what's impulse response. Impulse response is the response that the system produces when it receives the delta function. Okay, no response before time 0, before delta comes in. Okay. All right, so with that definition, let me mention that in this course, we're mostly interested in systems that are causal indeed. We are interested in systems that are causal most of the time. And we'll learn how to analyze a causal system, and we will also design causal systems. And when we say design, it means that we want to meet certain performance specifications, specifications. So far, so good? Yeah, causality. Okay, causality. And here's a note. So if we know that a system, an LTI system is causal, then this convolution equation can be slightly modified. Okay, let me explain. Y is equal to flip FH and multiply with X. That looks like a convolution for sure. But now the index only runs from -infinity to n, to the current moment. Okay? You know that before, in the previous slide, what is this index? In the previous slide, in a more general discussion, when we convolve two signals in time, that means we run the index from -infinity to infinity. Okay, the k here, the k inside can run to +infinity. But here we can stop at time n. To evaluate y of n, if n is represent the current moment, at any moment to evaluate the output, we only need the index to run from long before, from a long time ago, all the way to the present moment. Why? Because the current output does not, the present output, 现在, the current output will not depend on the future. The system, the future will not affect the current output. That's the spirit. 这是一个它的精神在这边啊。Yeah, that's the spirit. So that's why here you can just stop at n, because for any k bigger than n, for any k later than n, right? You immediately see that what happened to this term. This term here will be 0 for all negative time indexes, right? So nothing in the future will affect the current output. That's the idea. Okay, is that clear? So this one little nice thing right here. Stop at time n. There are actually so many ways to look at this equation. You can also think of this as if when we receive an x of n as our input, or let me say x of k, okay? Yeah, k equals to, so here you have an input signal and so on, okay? And then what is the output? The output at any moment n Okay, the output at any moment n is a summation. Is a summation from all the influences it receives from the past. K is the past, right? K runs from all the way long ago to right now, right? So that's the entire history. The entire history of the input would affect yn in a linear way. And this h is the linear coefficient. That's another way to think about it. Okay? Every past input would just affect the current output. And we sum them up, that's the way we calculate the output. Okay? Anything in the past can affect the current output. That's the idea. And with different weighting, okay, with different weighting. So each weight is represented in h. The impulse response will tell you how to calculate this summation. Yeah. So there's so many ways to ponder and contemplate on the result. I like the word contemplation. 凝视一下, contemplate your result. It makes a lot of sense, right? We cool? Yeah. 可以吗？好。那 with this, let's look at an example. Okay, so in this lecture, probably not in this lecture, but starting next lecture when we talk about difference equations. An important class of causal LTI systems can be defined by difference equations. 差分方程, sorry, not 微分, 差分方程. So here is an example that we will actually look at later, probably next hour. Difference equation. Okay, so here we have the current sample y of n. Right? Every current sample now depends on the past. In this way, you sum of the previous two samples. And probably the system also keeps receiving input x, right? So this defines a system, okay? It receives input right here, it produces output like recursively. There's also feedback terms, okay, if you will. 如果你这样说的话，也说得通啊, if you will. The output is the summation of the two past samples plus any input that the system receives. So that's a system for sure. Input, output, receiving input produces output. But then we can question. We can question, is this system linear? Is it time invariant? Is it causal? Yeah, so what's your opinion? Is this system linear? Is it time invariant? Is it causal? These are valid questions, right? These are concepts that we just learned, linear and time invariance and causality, right? Is it linear? Is it linear? If you double the input, will the output also double? So you can check these properties, okay? Seriously, so you can check whether the system is linear, okay? The answer is yes, okay? And is it time invariant? If we delay the input by 3 samples, will the output also be delayed by 3 samples? Right? Is it time invariant? Right? Is it time invariant? Okay. Yeah. So these are the questions that we can look at. And here, the equation specifies a system, right? Then we can immediately ask. We can immediately question: linear, time invariant, or is it causal? Is it causal? Does this equation produce any output before it receives any input? If the input is delta function, then does this equation produce any output before time 0? Yes or no? Yes or no? Okay. Anyway, so more general, this is just one example. This is just one example. But more generally, we'll study what is called linear constant coefficients difference equations. Okay, in the next lecture, where constant coefficients mean that here we have coefficient 1, 2, 3. We have 3 different coefficients. They happen to all be 1. 系数刚好都是1的. So you can change, you can generalize from here. the coefficients does not need to be 1. Okay, it could be any arbitrary real number. Okay, so in that case, we have different difference equations with coefficients, with constant coefficients, and we studied that. Okay, my answer to this, my short answer is indeed this system is linear, it is time invariant, and I would like to say it's also causal. Okay, yeah. I would like to say it's also causal, unless you are super creative. We'll cover that next in the next hour, right? So this is an example of a linear system, time invariant, and we can see it as a causal system, right? We'll come back to this, right? But next topic, let's officially introduce the Z transform, the Z or the Z transform. Okay, so we study Z transform. There's a reason why. The reason mainly is because we want to analyze the behavior of linear time invariant systems. So this is a tool. Okay, Z transform helps us understand and analyze properties of a LTI system. So we need to first let's move on to talk about the definition. Okay, so the definition is transform. So for any given sequence in time, n is a time index. Okay, for any sequence in time denoted as p. P of n, and n is an integer valued index. Okay, n is integer. So we can attempt to evaluate this expression. Okay, well, let's define this expression. We have a summation right here, and p goes here, z goes there, right? So the result, you just for any sequence p, small p in the time domain, we have a corresponding function of z. A function of z. And what is z? Z in most generally can be any complex number. Okay? Any complex number, and the summation index it sums over all n. Okay, so Pn can be from negative infinity to plus infinity. Okay. So I said this is an attempt to evaluate you can write down the expression. You can write it down. You can write it down. But I say we can attempt to evaluate the expression. That means that sometimes this infinite sum does not converge. It does not always converge. So let me say so. Okay. Of course, you can write down the expression, but it does not always converge. It depends on a few things. Okay. But first thing first, that's an expression. You can write it down. Yeah. Right. So we say that P of z, the big P, still we keep this convention using capital letters for the functions after transformation. This is a transform, much like it has a relation with Fourier transform. Okay, so transform, it goes from time domain to the Z domain. Okay, transform, just capital letter 大写, capital letter for the transform domain, and it's indeed called the Z transform of Pn, small p in the time domain. And this expression, 这边有点咬文嚼字, so let me read it. This expression is well defined only over the region where this equation converges, right? Otherwise, it does not make sense. Otherwise, it's just you write things down. Okay, it does not make sense. This really, because we really want this to be a function of z. Receiving, you can evaluate the transform at any one point on the complex plane. But sometimes it doesn't converge. Okay? It doesn't converge. There are a few criterions for if we consider convergence. Okay. But right now, I just want to just show you that the expression itself is pretty simple. Okay. For now, let's not worry at this moment for the region of convergence. For right now, but I do need to emphasize that it does not always converge. Okay. Depending on where z is and depending on property of P of n. Okay, we come back to that later. Any questions so far? Z transform regarding its definition is an expression. Okay. And here is a remark about the notation. Yeah, there is a relation between Z transform and the DTFT, the discrete time Fourier transform. Okay, so let me read it. DTFT really is the Z transform evaluated on the unit circle. DTFT is equals to Z transform evaluated on the unit circle. Okay, what is the unit circle? Unit circle is the circle with radius 1, okay, around the origin. Okay, so maybe I can draw a few pictures right here. So suppose this is a complex plane. We have the real part and the imaginary part. So the unit circle is a circle with 0, with origin being the center, and 1 being the radius,半径 or radius. Radius equals to 1, so you just draw a circle, the best you can, okay? Something like that. With a radius, topologically, this is a circle. Bear with me. 拓扑学上是一个 circle. Anyway, you get the idea. With a radius 1, so that's a unit circle. Okay. So I use this notation. I use the curly bracket, 大括弧. I use the curly bracket to denote a set. So here we have a set of points Z that can be parameterized by e to the j omega. Omega is the angle, omega being the angle, right? So e to the j omega is a complex number which has a radius of 1, which is 1 from, it has a distance of 1 from the origin, okay? So this is a unit circle. And it's called a unit circle because the radius is 1 unit, a unit circle, okay? So what does this mean? We say DTFT is Z transform evaluated on the unit circle. Why? Let's take a look. Okay, it's rather simple. That means when we evaluate the Z transform of X, the signal, on the unit circle by making the substitution, right? Z here just makes a substitution. Z equals to ej omega. That's what we mean. 在 unit circle 上面测量 Z transform or evaluated. Z transform when evaluated on the unit circle, yeah, just make the substitution, then you get this. Then you get this. And what is this? This is our friend, our good old friend, DTFT, right? Exactly the same. Simply by replacing Z with e to the j omega, right? So it's a substitution. We are evaluating Z transform if it converges, okay, only if it converges on the unit circle. Otherwise, the entire thing does not make sense, okay? But when DTFT exists, then we say when we need to add this criterion, okay? When the DTFT of the signal exists, when this expression and that expression really converges, when this expression really converges, then it equal to Z transform evaluated on with that substitution. 代入一下就可以了. With that substitution, Z transform evaluated on the unit circle equals to the signal's DTFT. And that's really nice. So that explains one strange thing right here, okay? In the textbook, remember all the way in chapter 4, and you've turned in the homework number 1, right? We recommend that we use this notation, big X spectrum, right? But inside, what do we put inside? We've been putting like rather inconveniently, 有点不方便了, right? Rather inconveniently. Inside, we put e to j omega. Why don't we just denote spectrum as x of omega? It's a spectrum, it's a frequency, it's a function defined on the frequency domain, right? So why don't we simply write this? Of course, this is not wrong, but just somehow in this textbook, Oppenheim and Schaefer, they prefer this notation just so that we have a consistent, a unified notation between DTFT and Z transform. Right? Because if you regard X as a Z transform, right? then when it is evaluated on the unit circle, that gives you DTFT. So that's the reason why we have this special notation that instead of that, this is simpler. Okay, this is in a lot of situations, this is actually simpler when you make derivation. 做数学推导, so this is simpler, right? But the textbook uses this notation instead, so that we have a unified, 一个统一的, we have a unified notation system between Z transform and DTFT, emphasizing that DTFT is Z transform evaluated on the unit circle. Okay, that's an emphasis. 就是特别去强调这个等效性啊。All right, we have a unified notation for Z transform and for Fourier transform, the discrete time version. All right, so that's so there is also an analogy, right? So and similar to now, may I ask a question? Now, the textbook also use this notation for continuous time Fourier transform, right? Why? Why do we need to write J here? Why is this notation preferred? Anybody? Why is this notation preferred? Why is this notation preferred? Okay. Laplace transform. Because now you have a unified, thank you. Okay, for those of you that are familiar with Laplace transform, how do we define it? X of S equals to summation, the integral x of t e to the minus st dt, right? So, so if we plug in j omega right here, then that becomes x of t e to the minus j big omega t dt. That's exactly the continuous time Fourier transform. Okay, so we have a unified notation between Laplace and Fourier transform, and by the same spirit, 同样精神. Similarly here, we have introduced this kind of notation in favor of being unified. Okay, so one nice thing to mention. Okay, yeah. All right, so notation definition, and then next thing is another definition. We are like throwing a lot of terminologies today. Okay, the next terminology is frequency response. The frequency response. We say frequency response of system. What does that mean? Again, for LTI system, that if the output, now we know that there's a system H which denotes the impulse response of an LTI system. And convolution theorem also holds for in the Z transform domain. When we have two signals convolving in the time domain, in the Z domain, the transform multiplies. Okay? Small h convolve with small x, big H multiplied with big X to produce the output Z transform. The Z transform of the output. Okay? And so a few terminologies right here, actually. H of Z, okay? H of Z, which denotes the Z transform of small h, okay? Now we can call it the system function. There will be examples, okay? System function, and then when we evaluate, again, when we evaluate this Z transform on the unit circle, then this, as a function of frequency, is called the frequency response of the system, again, if it exists, okay? If the DTFT exists, then it's called the frequency response of that system, okay? So let's organize our thoughts a bit, okay? We have a system first. And the system is characterized by its impulse response. This is LTI. Okay? All you need to know is impulse response. Then we just take the Fourier transform. If it exists, then we call it the frequency response. So the frequency response, in short, just briefly speaking, what is frequency response of an LTI system? frequency response, the frequency response is the Fourier transform of the impulse response. Long story short, okay? Long story short. So far, so good. Okay, about these, any question regarding these definitions? Frequency response, 频率响应 frequency response. But then, what's the implication? What's the insight that we can learn right here? So it's like we have the input in time, and there is an LTI system denoted as H, and it produces Y and M. And we know that H is specified. H is characterized by its impulse response, and that's all we need to know about the system. Okay? Sure, Y will equal to X convolve with H. But there's another interpretation. We can go to the frequency domain first, and then calculate the spectrum. Okay? And then what will H do? Then after the system processes the spectrum, you can think of now the output spectrum equals to H, the frequency response right here. This is the frequency response function, which equals to H it is the Fourier transform of impulse response. And then Y equals to the frequency response times X, the input spectrum at every frequency. Okay? So in the frequency domain, this is what is happening. Becomes multiplication. Okay? Convolution becomes multiplication in the frequency domain. And we might be able to agree that multiplication is an easier concept. It's easier to understand multiplication than to understand convolution, right? Can we agree on that? 小学时候有学乘法嘛，没有学 convolution, right? I don't think I've learned that when I was in elementary school. So this is a rather easier concept in the frequency domain. But then after that, what can happen? If you ever wonder, then we can take inverse Fourier transform to go back to the time domain. Okay, so that means Y equals to inverse dtft. Anybody? Inverse dtft. Okay, we can perform inverse dtft. Sure, from -pi to pi, and then Y equals to H times X in the frequency domain, and we synthesize the signal back to the time domain by collecting all the frequency components. Okay, quickly speaking. So that's the insight, okay? We have an LTI system, and we can first ask, then what does our input signal have at every frequency? That's its spectrum. The spectrum is a change of coordinate into the frequency domain. So every frequency has a magnitude, every frequency has a phase, right? But then now that in the complex plane, they are going to multiply with a frequency response. Okay? Going to every frequency, every component is going to multiply with the frequency response. So frequency response has two aspects. Let's come back to the slide, okay? So here I do want to mention that when you write Y equals to H times X, please remember that H in general is a complex number. It's going to be a complex number. So here we are talking about multiplication of two complex numbers at every frequency. At every frequency, this multiplication is complex valued. 是复数的乘法啊。So that's an important thing to keep in mind. So we need to be a bit more careful about when we say frequency response. We can talk about the gain, we can talk about the phase. Okay? We can talk about the gain, we can talk about the phase. The gain, what is the gain? The gain is when we take the absolute value of frequency response. Okay? Right? Okay? 好，可能需要点时间。Take your time, take your time. Before I can continue. or from here, okay? 1 over 2 pi, let's still keep developing this idea. Minus phi to pi, okay? So the gain we know that when we multiply two complex numbers, what's happening? What's going to happen? When we multiply two complex numbers, their absolute values will multiply. And how about their phase, the angle? The angle does not multiply, right? The angle add. The angle is summation. The magnitude is a multiplication. When we multiply two numbers in the complex domain. So here, if we emphasize that here h equals to its absolute value times e to the j, the phase of itself. 这有点符号有点乱啊。But you get the idea. Maybe I don't want to really emphasize this. Too much notation. Okay? Times x, which also has two parts. It's amplitude times e to the j, the phase part. And then we synthesize the signal back to the time domain by collecting everything in omega. So I'm just trying to say that the resulting signal right here will have this magnitude spectrum which multiply, okay? Then I'm just trying to say that the magnitude, or which probably is easier to go back here now. Anyways, when we multiply two complex numbers, the magnitude multiplies and the phase add. So the output spectrum, at every frequency, the output spectrum is going to be equal to the input spectrum times the gain. That's why we call this the gain. Okay, that's why we call this the gain that the signal will receive at frequency omega. And how about the phase? The phase means a phase shift because x angle, the phase of x is going to be added with, because the phase of the spectral frequency response is going to add to the phase of x. And that's the result. The result is the phase of y at every frequency. All right, so I was trying to explain the meaning, the insight. What does it mean to have a magnitude response and a phase response? Okay, maybe let's just go over with this. The absolute value right here means again a signal will receive at any frequency omega. And the phase part means a phase shift because phase is adding. Okay? When we multiply in the complex plane, phase is adding, so it's a phase shift. A phase shift. So we can refer to these two functions as magnitude response and phase response of a system. Okay, that's probably maybe all I need to emphasize right here. Okay, so I do have an example. Okay. For example, here we have a system. Okay, we can take a look. This is a system receiving input x and producing output y. Okay, then where we have a factor right here, t, and that you can regard it as the sampling period for a to d and d to a conversion. Okay. So now, this is there are a few exercises that we can do. First, is this system causal? Is this system causal? And whether or not it's causal, we can try to sketch the system's impulse response. And from there, we'll be able to calculate the frequency response if it exists. And if it does exist, we can again then make a drawing of the magnitude response and phase response. Okay, so there are quite a few things that we can do from this simple example. So we can do it maybe for a few minutes. Let's write a few things down first, and then we continue our calculation when we return in the next hour. Okay, so let's do a few things first. Y equals to xn minus xn minus 1 divided by t. Okay, so the first thing is let's try to derive the impulse response. Okay, so now if this is h, and now if it receives the input delta n, okay, delta n, what is the output? That's a question. Okay, that's a question. So you can do this. N equals to 0, h of n equals to delta 0 minus delta minus 1 divided by t. Seriously, that's what you can do. Okay, so h0 is 1 over t. And n equals to 1, we'll stop right here, and then we take a break of 10 minutes. H of 1 equals to delta 1 minus delta 0, right, according to the definition, divided by t. And that's 1 minus 1 over t, okay? So, and so on, right? So this way we can make a sketch of the impulse response. By definition, when the system receives the delta function, the output it produces is called the impulse response. So we'll return and do the frequency response part after the break.